talked about tangent slopes, correct? Tangent slopes touch in one spot. We've talked about that. It's the first derivative, correct? We've talked about that over and over and over and over and over. And if you actually drew all the tangent slopes that existed on that graph, you would start seeing how that graph would curve, correct? So just an aside, not writing on anything, but if you did a tangent slope on all the points, you might get something like this running. You do the tangent slope on that graph, right? If we do all the tangent slopes around that graph, what we might start seeing is a slope field doing this. If this was my slope field, what would I suppose that this graph's probably going to be? A parabola. It starts looking like a parabola, right? Sometimes they go like this, and then they go like this. Well, then they go like this. Then I was like, oh, maybe it's still a parabola, or maybe it's an absolute. So the slope fields help you kind of guess what your graph would look like. So if we go back to the first one here. This one says, match the slope fields with their differential equations. Now this is the crazy part. This is 0, 0, correct? That little line is a slope line, isn't it? What does this line have a slope of? 0. What do straight up and down lines have a slope of? Undefined. So when you plug in something, you get something over 0, right? Okay, what are these slopes? Negative. What are these slopes? Positive. What are these ones compared to these ones? These ones here are? This one's steeper. This one's not as steep. You see, like this would take, if you don't know what steeper is, think about trying to climb these lines. Would this one be easier to climb, or would this one be easier to climb? This one, this is not a steep slope, correct? And how do we get steeper slopes? Well, if my slope was 4 over 1, or my slope was 3 over 1, let's say, if I go up 4 over 1, that's my slope. If I go up 3 over 1, that's my slope. So the taller it is, the actual bigger the slope is, right? Now what if I did 2 over 3, something like that? Well, I would go up 2 over 3. But if I do up 4 over 1, it's much steeper, correct? So when your top number is actually smaller than your bottom number, you're going to have a less sloping line. Do you know what I mean? And then reverse and negative. Okay? Good talk. Oh, why would I just go use it? Not an anti. Oh, happy birthday. That was not meant to happen. That's because I use my left hand, and it's basically a useless appendage that I use every so often. I use it for catching a baseball, but like I'm just trying to aggressively lift it up to prove a point, and then I'm old. It would have been better if it just. Connor. It would have been. I would expect no different from you, Connor. I would expect no different. Okay. Let's look at 7. Yeah. So we have dy over dx of sine x. I'm going to take and plug in 0, 0, because I'm going to find out what I get when I plug in 0, 0. On all these graphs, if you look, this one you're going to get a slope of 0, this one you're going to get a slope of 0, this one you're going to get a slope of 0, this one you're going to get a slope of something big-ish. Big-ish. Super accurate. Okay, so let's plug in 0, 0. The only catch is there's no y on this, so I'm just plugging in 0, but it's still going to represent 0, 0. Okay? So I'm going to go dy over dx, and I'm trying the point 0, 0. I only just have to put in the x. So I get sine of 0. What's sine of 0? 0. So it's not a. I've narrowed it not to be a. It could be B, C, or D. Okay? Now what I'm going to do is I'm going to pick, I often try and pick the ones that are more like distinct. So like I would go here and say maybe I'm going to try 0, 1 because I'm going to hope for like a flat. This one's a 0 slope, this one's a 0 slope, this one has a negative slope, correct? So I can narrow myself down as to what graph it's going to be. If you're given multiple choice, you can narrow it down. If you're given a slope field and you actually have to sketch it, you have to put in every single coordinate. And just... You know? Okay. Yeah. So we're going to go 0, 1. What's the catch when I do 0, 1, guys? My x is still 0, and I'm only typing in 0. So what's going to happen when I have x of 0? It doesn't matter what my y is going to be. I'm going to get 0 slopes, right? So now I've narrowed it down to C or B. This one, all my x's and zeros have different slanty things going on, right? So it's either B or C now. So let's pick something else. We're looking at their slopes. So now we want to pick something that's different between B and D, or B and C. We want to pick something different between B and C. Look what I'm going to do. This is where I'm going to go with it. If I pick x of 1, they kind of look like they have the same slopes. X of 2, they kind of look like they have the same slopes. X of 3, this one has a negative slope, that one has a positive slope. Do you see that? So I'm going to test x of 3, then I can see if it's C or B. So I'm going to go 3, 0. It really doesn't matter what I pick for the y on these ones, but I'm going to go to 3, 0 and draw it. So it's going to be this one here that I'm going to attempt to draw. So I go dy over dx, sine of 3. Type it in, sine of 3. Positive. We get a positive? Yeah. So which one is it going to be? B. Now, guys, we get positive. Is it in degree or radian mode?
Which one is it supposed to be?
Radian.
I mean, C's sort of like curvy.
Sine of 3 is positive?
Yeah.
Is that
It doesn't have a negative.
It's hard because they didn't label the axes. It is C because C is going to curve, but it could be B.
No, look at C.
You guys, you're looking at this as a radian axis. If this is just 0, 1, 2, 3, 4, it could be B, a really zoomed in coast graph. Do you know what I mean? They need to actually label the x-axis so you don't know. Like we're looking at this and we're saying, well, this is going down, back up, but down. That certainly looks like a coast graph, correct? But we need to actually know what our x-axis is in.
Yeah, so we can't do it.
Chillax. This is just a discussion, people. This isn't like a freak out, start throwing pens.
Throwing pens?
We're not the one throwing these.
All right.
Yeah,
that was my accident. Okay, let's go to this one. We're coming back. We're just discussing. You guys have to have final answers at all times and everything perfect and they're happy. You can chillax for a few seconds. Okay. Now, if this was dy over dx is sine x, what was it originally? Negative cos. We have to keep that in mind. Okay? Now, let's go to this one. dy over dx is x. What would it have been originally? X squared, possibly. Maybe. Okay. So we're going to plug in zeros. When we plug in zeros, x of zeros, we're going to get zeros. So it's the same thing, right? If we plugged in 0, 0, we would get dy over dx is 0. If we plug in 0, 3, we're still getting 0. So all these will be zeros. So it's back to these two again. Then if we go dy over dx, let's pick a different one. Let's say 1. So 1, 0, we would get 1, right? Then if we plugged in 2, 0, we'd get 2, 3, 4, 5. These are getting really tall, correct? What if I plugged in negative 1? Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and starting to look like a parabola. So this one is actually 10. And this one is actually 7. The catch is this axis is not in it's in radian mode. It's not in like 0, 1, 2, 3, 4. This looks to me like it's in like 0, high, and then 3 pi over 2, you know what I mean? Like they made it in a radian, nice measure.
The actual test, will
They would have to tell you the scale. If the scale isn't 1, they have to tell you the scale.
and if they don't, can we?
Do you know what I mean? Like 0 pi over 2 pi is what it's doing. And then this is a negative coast graph because it's going down to -1, back up, right?
But if they don't give it to us, can we revolt, or like, can we get mad?
They will make it so it works.
You're allowed to throw in a eraser if that happens.
But most often I haven't seen sine or cos ones anyways. They're most often like 8, 9, and 10. So 8's a bit different because now no matter what coordinate I pick, I actually am using the x and the y. Do you see that? So say I pick 0, 0. This one is going to be 0 minus 0. So it's going to end up being a slope of 0. So at 0, 0, I should have a slope of 0, which has kind of narrowed us down to d, but we're going to prove why it is. So then say I pick 1, 1. 1, 1 is going to get me 1 minus 1, which is still 0. Wait a second, why are these all like this now? 1, 1, at 2, 2, at 3, 3, at 4, 4, 5, 5, 6, 6. Because you're taking x and minusing y, right? -3, -3, they're going to cancel. Okay, let's go and show another one. So I'm going to pick 1, 0. 1, 0 is going to become 1 minus 0, which is a slope of 1. And that's why these are all perfect y equals x lines. Do you know what I mean? Slope of 1 line. So do you see how slope fields just work? You literally just sketch them. So this one's 8. Now, 9, if we look at 9, the only points we're going to actually plug in, the only part that matters is actually the y for 9. I'll still write the coordinate 0, 0 so I know where to sketch my slope. But, yeah, what's up?
What's 1 minus 0, 0?
It's 1. I said 1 and wrote 0, and then drew 1. It's not 0. That's why you get these slopes here, the y equals x slopes. Okay, what if I plug in 0, 0 into this one? I'm going to get 2 minus 0, because I'm only plugging the y, so I get 2. So at 0, 0, I should have a slope of 2. Looks like it might. The ones that are like 2s and 3s and 4s are kind of hard to exactly specify, right? But I see that it's getting more steep. I see that it's getting less steep. I see that it's 0. So I'm going to test this one, because that'll be a good one, because it'll be 0, right? So I go to 0 and 2. And then I'm going to get 0 minus, oh, thank goodness. I was like, that's not working out. Okay, here, 0, 2. I'm like, this is not going to show that it's 0. What is going on? It's 0! Wow, look at that. Screw. Yeah. It's right here. I could check again. I could use 1 and 2. But I don't have to, because you're going to see that the y pattern of subtracting 2 off of 2 is going to give me 0. So that's why these are all going to be 0. Do you know what I mean? Slope fields, seriously, as long as you can take a coordinate 0, 0, plug it in, figure out a slope, be able to sketch it, you're in a much better boat. Okay? So I want you to just, for now, I want you to find me this one. Out of all of these. Find that. Which one is it going to match? Why would it match B?
Because it's the only one that has -1 and 0, I think.
It's the only one that has -1 and 0, 0. True. Also, I like testing the horizontal slope ones, right? So I have a horizontal slope here. You can't really see it, so I'm going to do this one. It's at 3 and -1. It is, could be a 2. It is a 2. Now, it needs to be a 2 because when I take 2 and I multiply it by 0.5, I'm going to get 1. And every time I do 1 minus 1, I'm going to get a slope of 0. So actually, every single x of 2 is going to get me a slope of 0, because the only thing I'm plugging into this one is x's, and 2 times 0.5 is 1. So you can actually decipher through by your algebra. Like the stuff that you're doing here for algebra's sake is not extremely hard. but it is hard to mess it up because there's so many different little lines on a tiny little graph. So often, if you're like getting stuck and you don't know how to do the slope field, like you're getting stuck on a slope field question, it might be of your best interest to ask for a separate sheet of paper or go on the side and like do like a little grid, 4x4 or whatever it may be, and sketch your own little thing and then go look and see which one matches. Sometimes it's better that way than looking at the graph because sometimes it's overwhelming. Up to you, however you do it. Okay. Ordering notes. I'll tell you what the homework is for that tomorrow. Tomorrow. Done. Yeah. Okay, section 5.4. It's still just properties of the definite integral. So we did definite integral for 5.3. We're going to just do it again. There's just more, it's like extended. And I talked about a lot of these properties already in the previous lesson, such as if you have a coefficient, you can actually take it outside of the integral. That's kind of what we're going to keep talking about today. We're also going to talk about total distance and total displacement as well today. Okay, so this is one thing. Theorem, we talked about this, but I didn't go into it in big detail. The integral of the sum of two functions. When we sum two functions. So if you had, like, for example, x squared plus 3x, that's summing two functions, x squared and 3x, which we did yesterday. We just did it as a full integral. Yeah, we just did the antiderivative of the whole thing, right? The theorem that they're going to state to you here is, remember with derivatives, when we did like the derivative of like 3x squared plus 2x plus 7, we could do the derivative of 3x squared by itself. Then we could do 7x by itself. Then we could do like d of dx of this, d of dx, and we could do them all by themselves, but we're like, why are we doing that? You could with integrals. So, if you have, for example, 0 or a to b of fx dx, or fx plus gx dx, we could just go a to b fx dx plus a to b gx dx. Now they always show these for a reason, and the reason why they're going to show this is sometimes on the AP exams, they don't give you like an actual x squared plus 3x, which we would just do the antiderivative of that fill in, right? We would use the fundamental theorem of calculus, which we did yesterday. That'd be totally fine. What they sometimes will do is they'll say, okay, find the integral of 1 to 7 fx plus gx of dx, where 1 to 3 or 1 to 7 of fx is 8, and 1 to 7 of gx is 9. So you would have to know that you can separate them and then just go 1 plus 9 is 10. Like they give you the pieces of it. So that's why we have to actually have pieces. So there's an example I'm going to show you. Will most often never do it this way, but I'm just showing you could split them up. Go with me. So example 1. Just like when we split up the derivatives and we were like, this is stupid, this is going to be this one. So we have 0 to 1 x squared plus ex, e to the x, dx. So using that theorem, it states we could go 0 to 1 x squared dx plus 0 to 1 ex dx, correct? It actually takes us way longer doing this. So I would assume no one's going to choose this option, but we're using this to lead into what type of question we have to use this for. So we go 0 to 1 x squared dx plus 0 to 1 ex dx. Neither of these have coefficients, so there's nothing I can take outside of the integral. So I'm just going to do the antiderivative of it. And I'm going to get 1/3 x cubed plus c 0 to 1 plus e to the x plus c 0 to 1. Normally, we would just go 1/3 x cubed plus ex plus c, 0 to 1, right? But this is just showing that you can split them. So, using fundamental theorem of calculus, we're going to go 1/3 1 cubed minus 1/3 0 cubed plus e to the 1 minus e to the 0. So we're going to get 1/3 plus e. And then logic will mess this up. What do we have to do? This cancels, but does that cancel? It becomes a 1, so I still have to subtract 1, correct? So I'm going to get e minus 2/3. Why did the c's cancel? Because you would add a c to this one, you'd subtract a c from this one. I showed that yesterday. Like you'd add a c, but this would minus the c, and the c's would just cancel off. You don't have to show the c's for fundamental theorem of calculus. Yeah. Okay. The other theorem we do. These theorems lead into extra help for us. So here's another theorem. I'm writing the short form versions just so you know. So this is for the integral of a constant times a function. We talked about this yesterday. We even used it. So if k is a constant, so it could be 2, 3, 4, 75, 82, negative 7, right? If k is a constant, and we have a to b k f of x dx, what did I tell you we could do? Yeah, so we could go k a to b f of x dx. So example 2. It's not negative, it's example 2. I'll put dots because it looks like I just put a negative outside it. Now a lot of people won't even spot that this is a constant. I know how to take the antiderivative of 1 over x. The antiderivative of 1 over x is ln x. That's easy. The antiderivative of 3 over x, but I can turn, I'll show a middle step in here, which I normally wouldn't, but I'm going to. 1 over e, 3 times 1 over x dx. I can rewrite it like that, can't I? And then where can the 3 go? Outside. And then I can do the antiderivative of that. And the 3 just sits out front until I'm done, and then multiply it in. That's it. So I'm going to get 3, bracket, ln absolute value of x. And I have to use the absolute value of x because I can't put a negative or a 0 beside ln. And I'm going to fill in 1 to e. So I'm going to get 3. Oh, sorry, plus c. There's a little c in there. You can see it. We're going to get ln of e minus ln of 1. What's ln of e? It's just 1, because it's log of e, right? Which is 1. And minus ln, what's ln of 1? Just ln of 1. So what am I going to get? 3 minus 3 ln 1. Actually, ln of 1 is 0. Because ln of 1 is log base e of 1. E to what power is 1? 0. So what happens to this whole thing? The answer is just 3. So watch yourself. If you get an answer, but it doesn't match, and you know you did everything right, go back and be like, wait a second, what about the ln of 1? Maybe that's not there. Okay. What about this? Example 3. find 1 to 2, 3x cubed minus 6x squared minus 5x plus 4. We're going to use something that I reminded you in derivatives. 2x dx. What did I remind you in derivatives? I told you, if we have a monomial in the bottom, don't use quotient rule. You can bring it to the top, but now you're doing integrals with power rule, which you also don't know how to do. What else could you do? Right.
Oh,
Like break it up and throw it in your calculator.
No.
Yeah.
Nope. I love how you guys are going really advanced. This is not.
Just back
No. Nope.
You start.
You just divide, you guys, this is what I told you, over and over and over in trig. This is a basic rule from junior high. You guys are really good. If I give you something over 2x 4 times, you know that you guys can put it together and put it all over 2x. Right? What I told you guys often forget is that you can just put them all, each one of them, you can separate it. You can put every single one of them back over 2x. And when you do that, you get rid of the denominator. There's no antiderivative tops and bottoms. There's no deriving. I don't know why we're deriving. It's an antiderivative. Some people are giving that as options. It's when you derive, it's L'Hopital rule, and it's a limit. There's no limits on this. There's like that's never an option for this one. Okay. So remember that when you have a monomial in the bottom and you're deriving, or you have a monomial, like because it's polynomial or a polynomial technically, right? Polynomial or a monomial. Monomial is a type of polynomial. You have to remember to write them all over each one, over 2x. And then you get rid of the denominator. It goes away. So let's do it. So we're going to get 1 over 2. So you're good at putting fractions together. You forget that you can pull them all back apart. So we get 3x cubed over 2x. Minus 6x squared over 2x. Minus 5x over 2x. Plus 4 over 2x. Yeah. It looks worse now, but you're just going to reduce. This x cancels off this one. So I'm left with 3 over 2x squared, which you can do the antiderivative of. 2 and 6, we're going to cancel, make it a 3. This one cancels off one of those, so I'm left with 3x minus 3x. These ones, the x's cancel, I'm left with minus 5 halves. These ones, the 2's cancel off, I'm left with 2 over x. Dx. Now we can use both rules that I just taught you. Sometimes it's easier to actually make them all separate integrals if it's overwhelming when they're all together. Okay? Because sometimes you want to have the coefficients out. Up to you, it doesn't really matter. We can do it either way. Now, what we're going to do, when we have 2 over x, what's it going to turn to? So, yeah. So when we had 3 over x, right, we ended up with 3 ln x. That's what we ended up with. So that's going to be the hardest one on here. The rest you're going to find hard because there's fractions, but not because it's actually hard. Okay? You guys just see fractions and start freaking out. You have a calculator in front of your face. Okay, so we have 1/2. Now we have 3 halves here. Remember, if it was overwhelming, how could we do this? We could take the 3 halves, we could put it in front. So I'll go that route. And we could go 1 over 2 x squared, because x squared isn't overwhelming to me. Minus 3, 1 to 2 of x. This one's literally just a coefficient. And then this one would be ln x. I don't find this easier personally. When it's just polynomials, I don't find this easier. I find like, where am I putting numbers in, what's doing this? I will never choose this route. You can go that route. You may think it's easier. It's not. Let's just try it the normal way. Because you can choose it. So, x squared becomes what? X cubed. And then you do 3 halves divided by 3. Or 1 over 2. So we get a half in front. Then this one, it's going to become minus x squared. And then what are we going to get in front? 3 over 2. So like I said, you can do it this way. If it's a polynomial, I will just always just do the integral. Minus 5 halves. It's x to the what currently, guys? X to the 0. So what's it going to become? X to the 1. If you write x to the 0, people can do this question. If you don't write x to the 0, people will stare at it and go, oh crap, I don't know how to do this. Okay? Why do I know that? Because people will call me over the test and be like, you never did this. And I'll be like, we did. And we never did this. Okay. So x to the 0 returns to an x to the 1. And then I divide 5 halves by 1, and I get 5 halves because divided by 1 is nothing. And then we know 2 over x becomes 2 ln absolute value of x, 1 to 2. Let me just plug it in. Oops, plus. I keep putting really teeny tiny things in. Okay. So we're going to get 1 half, 2 cubed, minus 3 halves, 2 squared, minus 5 halves times 2, plus 2 ln 2, minus 1 half times 1 cubed, minus 3 halves times 1 squared, minus 5 halves times 1 plus 2 ln 1. What's ln of 1? 0. I should put a line because that looks like a 1. It's not. It's 0. So here we're going to get 8 divided by 2, which is 4. Here we're going to get 4 times 3, which is 12, divided by 2, which is minus 6. Here we're going to get minus 5 plus 2 ln 2. And the minus sign is going to have to go through. So I get minus a half, plus 3 halves, plus 5 halves, and then technically plus 0 if we want to show that. When we put them all together, you get negative 7 halves, plus 2 ln 2. Okay, this is where the splitting actually matters. I want to get through it so that you can see where it's more helpful. So this is another theorem. Sometimes they'll give you this. So we go a to b of f of x dx. And they're going to give you an a to c and a c to b, but they're not going to give you the answer to a to b. What the heck does that mean? I'll show you. So they'll give you something like this. I'll just do a little graph. We'll go. And then this would be my A. This would be my B. We agree? But they don't, and this is my area 1. But they don't actually give me A to B. They give me a C value somewhere in here, and they'll say area 1 is this, area 2 is this, give me area 3. Like, give me the combined area of 1 and 2. Right? They make it a bit more complicated. So how do we do that? We go still low to high, so we're going to go a to c, fx dx, and then we're just going to add c to b, fx dx. That's the only difference. And people are like, why the heck would I ever do that? Because they force you to. You'll see why. If they give me 1 to 9 of like x squared, I'm not going to ever split it, right? That's not where it's going to come in half. They'll give you something like this. So I give you this, example 4. This is A. If f is integrable, that is a word. Means you can take the integral of it. Integrable on, it sounds like it's made up, it's not. On the closed interval 2, 7. Then determine two to 7 fx dx given 2 2 to 4 fx dx, to make it up, is 3. And then I'm going to go and 7 to 2, that's a lie, 7 to 4 fx dx is negative 2. How can I set it up? Yeah, you're going to go 2 to 7 fx dx equals, we have to go 2 to 4 fx dx plus what? Nope, plus, what does it have to be here? What number has to be here? 4 to 7 fx dx. We're just setting up the equation. I'm literally just writing out the formula if I was doing this. I'm not using any of this. You're going to have to flip this. I do not need to flip this. This is the formula. If I'm going from 2 to 7, I have to go 2 to 4, then 4 to 7. That's what I literally just wrote up here. A to C, C to B. That's the formula I have to use. You guys are correct in saying that I did not give you that information, but this is the actual formula I have to use, correct? Okay. So, good. 2 to 4 fx dx is 3. I'm not changing this. This has to be 4 to 7. That is not a, this is a no-go. Like, I have to go 2 to 7 is 2 to 4, 4 to 7. That is a true statement. We agree? However, I did not give that to you. So I do not make this negative and adapt it to that. Which is what you guys are trying to do. I don't make this negative and adapt it to that. I make this be what I need it to be. I need it to be 4 to 7. So what am I going to actually make this be? 4 to 7 then of fx dx must actually equal what? 2. That's the one you change. You don't change the one in the question that has to be this way, right? You change what I gave you and you're like, thank you for that information. Somewhat helpful. Need to change it so I can use it. So now I just go plus 2 and I get 5. So this is where the piece part comes in handy. This is where you actually have to split them because they give you only 2 pieces of information and they're split pieces. Like you can't do the whole because they don't give you the whole. Make sense? Okay. Example 5. I'm not doing B. We're in a bit of a rush. We'll pretend that B existed. It happens. There you go. Example 5. Because I want to get up to the mean values there. So example 5 is find the area. And the find is stupid. Oh, there it is. Find the area under the graph of, now this is another way they can do it without just directly giving you the answers. When they directly give you the answers, people will sit here and stare at it. I'm like, the easiest question, just do it correctly. Okay? This is another way they can ask it without just nicely giving you the answers to the area. So they'll go f of x equals, and it's going to be a piecewise function, x squared if 0 is less than or equal to x is less than or equal to 10, and f of x equals 100 if 10 is less than x is less than or equal to 15, and then you want it from 0 to 15. So what do they want? They want the area under the curve. They want the integral from 0 to 15 of f of x dx. We agree? Problem, up until this point, I've given you f of x is x squared plus blah, 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 and you just do the antiderivative fill in, correct? This time I'm giving you a piecewise. I'm saying, okay, f of x from 0 to 10 is x squared. F of x from 10 to 15 is 100. So how can I write out this equation to use it? I'm going to go from 0 to 10, and what am I going to put here? X squared dx plus 10 to 15, 100, x to the 0 dx. I always put x to the 0 behind it because if you put x to the 0, everyone will get it right. If you don't put x to the 0, half of you will stare at it for a while, and it's the easiest one because you just raise it to the power 1. Because remember, constants just become the term with an x, right? Because x terms just became constants. Constants just become terms of x. So let's go do the question. So we're going to go, what's the derivative of x squared? 1/3 x cubed plus c 0 to 10. Plus the derivative of 100x to the 0 is 100x is raised by 1 divided by 1. plus c, 10 to 15. Is this really a hard question? No. I actually think it's easier than some of the other integrals we do, because they give you nicer functions. They're nicely like piecewise. It's not like 8 terms. It's like 1, maybe 2. So we plug it in. We get 1/3 10 cubed plus c. I don't need the c's. Told you that already. And then I did it myself. Minus 1/3 0 cubed plus 100 times 15 minus 100 times 10. So I'm going to get 100 over, 1,000 over 3. This becomes a 0. This is going to be 1,500 minus 1,000, so minus 500 plus 500. Is 2,500 over 3. Is that so hard? I actually find these ones easier, piecewise integrals. I want to show you one when it does this. Example 6. Determine, I can't write find again, I've wrote it too many times, it's driving me crazy. Determine -1 to 4. I just have to show you this one because there's a catch. The catch is not a hard catch, it's don't try and do something with it catch. Okay, so we have f of x. What? I can't go from the bottom, that just didn't work at all. E to the x if -1 is less than or equal to x is less than or equal to 0. 5 if x equals 2. And then x plus 2 if 0 is less than x is less than or equal to 4, x can't equal 2. How much area is under a dot? None. So what are we going to do with this 5 and this 2, 5? It's lovely, but I don't care about it. The graph looks something like this. I'm going to do a really quick sketch. It goes like this for the E, and then it goes like this, and then up like this, and then at 2 there's an open dot, and then there's a closed dot here. So really what we're doing is we're finding the area under here, the area under here, and thank you, dot, don't care, because it would just have an area of 0, right? Like it's just, so we would go, but we still would have to split it. You still have to show the split. Why do you still have to show the split? Because this one still doesn't equal 2, correct? So you would have to go -1 to 4 fx dx equals -1 to 0 of e to the x dx plus 0 to 2 x plus 2 dx plus 2 to 4 x plus 2 dx. Why can't I show it across the whole thing? Why can't I go 0 to 4? This equation doesn't include the 2. So you're going to get e to the x plus c, -1, 0.
So even though it's just greater than and not equal to x plus 2, we can still have it.
Right, because the endpoints don't really matter. They're going underneath it. And then this is going to be 1/2 x squared plus 2x plus c, 0 to 2. And then 1/2 x squared plus 2x plus c from 2 to 4. E to the 0 minus e to the -1 plus 1/2 to the 2 squared plus 2 times 2 minus 1/2 to the 0 squared plus 2 times 0 plus 1/2 4 squared plus 2 times 4 minus 1/2 to the 2 squared plus 3 times 2. Just a lot of numbers, but it's the same steps over and over. And when you do that, you get 17 minus 1 over e. Because this here is going to become a 1 over e. That's going to become a 1. So don't forget this is a 1. So there are a few things we need